Hello, everybody, and welcome to today's geology meeting. We're very lucky to have Martin Eales with us, who is the Geology Advisor for the U3A, amongst many other things in your privileged and esteemed background, I believe, Martin, in terms of geology. And Martin is going to be talking to us about the rocks of Britain in the Palaeozoic, which is the era of early life. And he has asked if you have any questions or comments, could you please put them into the chat during the talk? There will also be a short break at some point, and we will have questions later on. So what I will do now is put on everyone onto mute, apart from Martin, and hand over to you, Martin.
Good. Thank you very much, Mary, for that introduction. So I'm aware I'm talking to the geological group, the top of your U3A. I do have a few of the introductory slides, so I'll go very quickly through those. So hopefully you can see the first slide, the title slide, The Rocks of Britain, the Palaeozoic. That's 300 million years of history. And what we'll do is having a geological voyage through this ancient time. So from 550 to 250 million years. Palaeozoic, it's all Greek, of course. So paleo is for ancient, and then zoic for life, ancient life. I show this slide up really as the first slide, just to remind you on the geological eras. So the world started, you see, around about 4,500 million years ago. And it's not until around about 10 o'clock on this clock, you see, we are really talking about life, complex life as we know it. So that started with ancient life, the Paleozoic, did around about 500, 540 million years ago. And then we have the Mesozoic, Greek for middle life, and the Cenozoic for recent life. Right at the top, you can see humans. Those are just the last 2 seconds on this clock. And so we're about 12 o'clock now. So it's high noon. Perhaps we've got, with luck, another 4.5 billion years to go. These are the geological periods. I tend to like to think the eras, which I've just talked about, perhaps as dynasties, Tudors, Stuarts, Georgians, and that sort of thing. But then we come on to the periods, perhaps think of those as our monarchs. Essentially 11 periods. So within this last time of 500 million years or so, each one is about 50 million years. So the Paleozoic, you see, we start off with the Cambrian, then Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian. I always think we really have to know these periods well as geologists. So if you don't know them off by heart, recite them in your sleep much better than trying to recite sheep, for example. So the start of the Paleozoic, this was really when we had the first hard fossils. So this is the Cambrian. But it was also when we had the first fish, animals with backbones. So as we progress, you see Silurian, the first plants, Devonian, amphibians, Carboniferous, first reptiles, Permian, a lot of diversification. To start with, this was a great time, but then an extinction, the great dying right at the end of the Paleozoic. And then, of course, we move on to the Mesozoic, first mammals, dinosaurs, and then, of course, the extinction, mass extinction at the end of the Cretaceous. So I've mentioned extinctions. Extinctions happen all the time. So this slide, you see on the horizontal axis, it's millions of years. Now on the right, on the left-hand side, is the start of the Cambrian, the start of the Paleozoic. And then the vertical axis is extinction intensity. So as you see, extinctions happened all of the time. But right at the end of the Paleozoic, you see we had the great dying event, where some 95% of life perished. Then we went on to the Mesozoic era, and at the end of that, again, we had a mass extinction, and you can see the end of the dinosaurs. But extinctions happen continuously. This is a summary geological map of the British Isles. So I'm sure it's just recapping for you. In the north and west is essentially the Precambrian rocks, especially the Scottish Highlands, the peripheries of Ireland. Our Paleozoic rocks, mainly southern Scotland, northern England, western England. And then the Mesozoic, more in the south and east. And then we do have little bits of Cenozoic, the London Basin, the Hampshire Basin, for example. But we're really lucky, I think, in this country in having such a variety of rocks, really all different ages. Some of the very oldest rocks, for example, extreme northwest of Scotland, to some of the youngest. How do we name these geological periods? All of the periods in the Paleozoic were named by British geologists. Really, it all started early Victorian times. We had Adam Cedric, who was roaming around North Wales, and he named his rocks he saw Cambrian, after the Welsh mountains. And then we also had Murchison, and he was working essentially in South Wales, and he called his rocks Silurian. Clearly there was a difficulty when they both met. So Murchison, you see, encroached his lower Silurian on Cedric's upper Cambrian. So what should we do? So here we have Lapworth, 1879, the compromise. He called the rocks in the middle Ordovician. So you see, these are all Welsh terms: Cambrian Mountains, the tribes, the Ordovician tribe, the Silurian tribes. And all of these periods are used worldwide. So if you talk to somebody in Brisbane or Beijing or Vancouver or Vladivostok, they'll always use these names here which originated with the early Victorians and the start of the Paleozoic, names from Wales. This slide shows the varying temperature over geological time and actually the CO2 levels. So the temperature is in blue, CO2 in black. So the horizontal axis goes essentially from the start of the Paleozoic on the left, now is on the right. And then the vertical axis shows average global temperatures and the CO2. So just look at the blue line. Generally, it's relatively constant. I mean, obviously this is a smooth curve, but relatively constant throughout these eras. We had ice ages, at least 3 ice ages, and those I've highlighted in red. So at the end of the Ordovician, quite an intensive ice age you see in the Carboniferous and Permian, and an ice age, of course, now. We are in an interglacial, but we are in an ice age. There are ice at the poles, and this is very rare. Really, as you see, only happened about 3 times. So virtually all through the geological history over the last 500-600 years, it has been a lot warmer than it is now. Have a look at those CO2 levels. You see very high at the start of the Paleozoic and then decreasing throughout the Paleozoic, getting very low in the Carboniferous and Permian. Increasing a little bit, you see, during the Mesozoic, but it's very low now, anomalously low. Certainly, with the results with human activity, it has increased, perhaps at least 50% more than during the ice ages, but it is still a lot lower than it usually has been over the last 500 million years. The slide at the bottom now just shows the oxygen level. You can see the oxygen was fairly low over a billion years ago, and then increased rapidly just before the Cambrian. From the start of the Paleozoic, you can see it's increasing throughout the Paleozoic, and very high, especially in the Carboniferous and Permian. Then a rapid decrease at the end of the Paleozoic. Then you see an increase again in the Mesozoic and a decrease essentially in the Cenozoic, and it's relatively low now. So a great time to live, if you wanted to, at the end of the Paleozoic. So if you were an insect, especially an amphibian, marvelous time to be around at the end of the Paleozoic. Lovely high oxygen. And if you were a dinosaur, again, in the Cretaceous, a great time to be alive. I won't dwell on this slide. I'm sure you all know about the rock cycle. But three main types of rock, of course, igneous, sedimentary, metamorphic. Mainly, I'll be talking about sedimentary rocks, but a little bit about igneous and metamorphic. And just summarising that now on a map, you see most of England, southern Scotland is sedimentary. Bits of igneous represented by the purple and the red, the volcanic and granites. And a little bit of metamorphic you see in North Wales, a little bit possibly in the Lake District, peripheries of Ireland, but mainly the Scottish Highlands you see is metamorphic rocks. The classification, and I'll be talking about this a little bit more with our slides as we go through the history. So, as I expect you know as geologists, three main types of sedimentary rocks: clastics, caused by erosion, chemical, seawater evaporation, and the biochemical, mostly carbonates, animals, and plants. And I'm sure most of these names that you are familiar with. I think where you are, it's right on the edge of the chalk and possibly going into the lower Cretaceous, but as well. So chalk, limestones, and sedimentary rocks, the sandstones, the shales. And what I do encourage people, and I'm sure that many of you do, wherever you live, you can look at any building stone and you can speculate when that rock was made, deposited, and what the environment was. Any sedimentary rock is going to be deposited in one of these environments. Anywhere from the mountains, the glacial environments, lakes, on the continent, within rivers, shelves, the continental slopes, or the deep marine. And so you should be able to look at the rocks, I said, in outcrop or any building, which is building stone, and have a very good idea how that rock was deposited. Good, so that's a very rapid introduction now. So let's start with the Cambrian. So this was the paleogeography at the time of the Cambrian. And you can see that England and Wales was really right in the far south, attached to Africa, actually, which was in the southern polar regions. And so England and Wales was really cold. Siberia, you see, was quite nice and warm. Scotland was really attached to North America, so around the equator. So it was nice and warm and balmy then. So England and Wales really quite cold in the far south, Scotland around the equator, and separated by the Iapetus Ocean. So a huge ocean, much larger than the Atlantic is now, of course. And what we'll see that throughout at least the lower of the Paleozoic, England and Wales decided they didn't want to stay as cold as this. Let's move rapidly north and join up with Scotland. The early Cambrian fauna, quite a bizarre lot that as you see here. Some very small, some quite massive. Much of the fauna, perhaps we don't really know a lot about. You see this lovely little creature, which I put right up in the top right here. Actually, which way up is it? How does it walk? Has it got spines? Has it got legs? We don't really know, but lots of bizarre creatures, especially sort of just before the start of the Cambrian and Infracambrian and the start of the Cambrian. So the Cambrian in northwest Scotland, as I've said, it's nice and warm there, but hot, shallow. What sort of rocks do you normally get? Shallow marine conditions, limestones. The warm sea, this is first life here with shells. So this is the Durness limestone. So if you go right to the north of Scotland, the far north, you have these limestone cliffs and limestone caves. But now moving further south, for example, in Wales, have a look at the building stone. Don't take your hammer to these castles or cathedrals. But this is the sort of the building stones in Wales, deep marine plastic sandstone rocks. Excellent, you see, in building castles and building cathedrals. And in Wales also, you have slates. So virtually all of our slates at one time came from North Wales. And the conditions here were then deep marine, fine-grained rocks, shales, and then low-grade metamorphism, converting those to slate. Now we move up to the Ordovician. This slide shows essentially the paleogeography, middle Ordovician now. Can you see England and Wales are starting to move up northwards now? The Iapetus Ocean is closing. Africa, you see, is still right in the far south. And the Sahara Desert at this time is covered in ice. A few years ago, I was in the Sahara Desert looking at glacial deposits. It was well over 40 degrees, but we were looking at the tillites in the Sahara Desert. You see, Antarctica is around the equator. So closure of the Iapetus Ocean. So this was happening in the lower Paleozoic times. So you can see England, Wales, Southern Ireland, and also Newfoundland, most of Nova Scotia, most of New England. They were with England, Wales in the far south. But north of the Iapetus Ocean, you see we have Scotland and the northern part of Ireland and Newfoundland. And those were all connected to the American continent. So closure of the Iapetus Ocean. In other words, you must have had subduction. You must have had trenches. What do you then get? You get volcanics. So Ordovician volcanics in England. Essentially, if you go to the Lake District, you go to North Wales. So we have significant volcanics in the Lake District, that either Scafell Pike is essentially Ordovician ash, and so is Snowdonia in North Wales. And there you see, I've just shown some pictures on the top left. You have Scafell Pike, and then the Snowdonia with Beaumaris Castle in the foreground. The Ordovician volcanics associated with closure of the Iapetus Ocean. What else do you get in the Ordovician? Igneous intrusions in North Wales. And for example, you have these bluestones, marvelous ornaments, quite sacred and useful for building stone circles like Stonehenge. So transported, as you see, well over 200 miles from Pembrokeshire to Stonehenge in Salisbury Plain. Life in the Ordovician. This was especially the evolution here of the calcium carbonate skeleton. But not only corals, crinoids, and the like. Probably many of you have heard of trilobites. Trilobites, you see, come in all shapes and sizes. Think of these as really woodlice, often giant woodlice, crawling about on the surface of the sea floor here. And I really like this slide on the right, where you have these trails, these grazing trails. Actually, in my house here, I've got some fossils of grazing trails of trilobites, which I got from the Libyan desert here. But you can see they love to graze along these lines, not very good for social distancing. Graptolites. Now, as with trilobites, graptolites are extinct, but they were very, very common fossils in the lower part of the Palaeozoic here. Tend to think of many of these perhaps as tuning forks. You can see a typical tuning fork on the top center here. So graptolites essentially floated around the surface or near surface of the ocean. And you had lots of different types of graptolites, which I perhaps indicated on the slides, the top right and the bottom right, and they evolved very quickly. And they really are important in trying to date our rocks. So geologists still tend to date rocks using the fossils. We can tie that in often to absolute dating with radioactive means, but still our main weapon is looking at the fossils. And graptolites, especially in the Ordovician and Silurian, evolved very quickly. And so we can date rocks pretty well, certainly within a million or less than a million years. The graptolites said that these are colonial creatures. if you like, perhaps more analogous to corals, but not with a limestone frame or shell. But you can see you had little creatures in each of those little serrated lines I've shown you, a little creature called a zooid. They're all extinct by the end of the Paleozoic. Right, now we move on to the Silurian now. So we're moving rapidly on, and England and Wales has also moved rapidly northwards. So now we can talk about the United Kingdom. So by this time, England, Wales, Southern Ireland has collided with the North American, the continent. But you see that Africa is essentially still around the South Pole. And Antarctica is just starting to move southwards. Australia, you see, is around the equator. Note actually, that's a point to note, because I could have said, even with the Cambrian slides, how much is covered in water. Sea levels generally were a lot higher than they are now. Sea levels are anomalously low. So if you are on the edge of the chalk throughout now, for much of the time, you would have been underwater here. And it probably is only around the tops of the Pennines, for example, that in England, that wouldn't have been covered in water. Silurian life. So the first land plants, for example, and they were moving across the land. We had fish with jaws for the first time. And the fish, also some fish, were starting to move onto land, into fresh water. And we had these bizarre things as well. Now, what on earth are they? I've titled fungus trees or mega rhizomorphs. They're called prototaxites, essentially mainly Silurian and Devonian times. Now, we really don't know much about them, but you can see and look at this slide in the bottom right. They were huge. They became extinct essentially in the upper part of the Paleozoic, and we assume this is because of the evolution of vesicular plants. But they seem to be more linked with fungi. But so did they grow upwards? Or, as some people I think are tending to think more and more, did they really grow more horizontally? And you can see the note I put at the bottom here. Then perhaps very large sort of structures, not that different actually from modern fungi, where you have a lot underground and helping the redistribution of water and the nutrients, and even perhaps facilitating the expansion of land plant communities. But see, potentially these were very long or very tall, 8 meters long, a meter thick. Southern Scotland. Southern Scotland, we call this an accretionary complex or an accretionary prism, formed essentially at a trench. And this is really the main ways how continental crust is created. You can see the line here, which has got the chevron. I don't know if you can see my cursor here. So this is the Iapetus suture. So essentially, south of that line, we had England, Wales. Then we had this accretionary prism, which separated it from the North American Scottish plate. And just in purple, can you see what I've called the Ballantrae ophiolite? So an ophiolite is where we have oceanic crust thrust up onto land. So this is the remnants of the Iapetus Ocean. You can go to the little village on the coast, Ballantrae, and you can see this little bit of oceanic crust from an ocean that said was a lot bigger than the Atlantic Ocean. There it is at Ballantrae. This is an accretionary prism, accretionary because it consists of slithers. You see sediments which are pasted on to the continent. So just imagine with this slide, this is the southern uplands of Scotland. So on the left, we have the Midland Valley, Glasgow, the Scottish plate. On the right, England, but going to Carlisle. And you see the trench here, the subduction zone. The first slither you see is one on the left, and then each slither as we go then to the right gets younger and younger, separated by these thrust faults, and we have rotation as well. These sedimentary rocks are rotated. So essentially they started off as trench sediments and then coarser sediments within each slither. So the southern uplands of Scotland, an accretionary prism. And you can go to the southern uplands of Scotland and see some of these initial fine-grained trench sediments, deep marine shales. And you can go to a classical exposure called Dobbs Linn, which is near Moffat, right in the central part of the southern uplands here. And this is a very famous location for geologists. It's what we call a global boundary stratotype section and point, which is a heck of a mouthful. Well, just think of it as a golden peg. So this is the world boundary, or where everybody in the world defines the boundary between the Ordovician and the Silurian. The golden peg at Dobbs Linn. And it's a very good exposure because we had lots and lots of graptolites. I show a graptolite, typical graptolite, that bottom left. So they evolved very quickly. And so we can see how they evolved across the Ordovician and Silurian. So if you wanted to know where the boundary is defined and you live in Beijing, you go to Dobbs Linn in southern Scotland. What else do we have in Scotland? This is again associated with the subduction zone. Closure of the Iapetus Ocean, subduction, what do you get? You have granites. So you can see a lot of granites in Scotland, southern Scotland, the Scottish Highlands. Aberdeen, if you've been there, a lot of buildings are made of granite. But you might think of this as the granite city. And Ben Nevis is granite. See, all of the granites here are shown in red on this slide. So subduction, granites. So now we're going to the Devonian time. See, we've moved up rapidly. We've gone around about 150 million years. So what do we have now? The continents have collided. We have mountains. In the north, you see high mountains and the deposition of old red sandstone here. Red, essentially because it was deposited on land. So the iron gives this red colour, and it was obviously hot. So on land, deposition mainly by braided rivers here and the red sandstone. Right in the far south, see in Devon, so obviously that is where we get the name Devonian from, we have limestone and lots of fossils, which again help with the dating. So here it was warm, but it was marine, shallow seas, warm seas in the tropics. What you have carbonates. And Devonian life, the age of fishes. This is when the fishes really evolved during the Devonian times. But not only fishes, of course, life again was starting to get quite large at this time. You see these eurypterids. Perhaps you can think of these as giant scorpions here. So on the top right, this is an example which found in Germany. See, shallow marine, they're carboniferous, of course, but they declined after the Devonian, outcompeted by fishes, and then became extinct completely at the end of the Permian. But see how large these were. Wouldn't it be awfully nice, perhaps, if we were swimming around this ocean and we sort of came across one of the eurypterids? But is this the largest arthropod which has ever existed? Possibly so. 3 meters long, you see. We have excellent building stone from the Devonian. We talk about the old red sandstone. Where can you go? For example, the Welsh borders, southern Wales, the Hereford. You can see it's mainly the cathedrals, bridges, and so on, made of old red sandstone. Tintern Abbey, old red sandstone, all deposited by rivers. Rivers because it was land, land because of the closure of the Iapetus Ocean. What about Scotland here? Again, we have the old red sandstone that deposited in rivers and lakes. So think of Glasgow, a lot of old red sandstone buildings, actually beautiful Victorian buildings, which now have been cleaned up. So old red Devonian sandstone. And the abbeys in southern Scotland, Jedburgh Abbey, for example. You can go up to Orkneys, and I'm sure you've all heard of the Old Man of Hoy. Again, Devonian sandstone. You can see how the beds here very well layered here. But much of this in the Orkneys was actually a desert lake. And I show slides here of Skara Brae. If you've ever been up to Orkney, you might have visited Skara Brae. A lot older than Stonehenge or the pyramids. Made of stone. Beautiful rocks, you see, for building and making your household furniture. These flags, easy to cleave, lying on the seashore. So great to have your huts, and you can see whatever you wanted, dressers, beds or so. This Devonian sandstone was ideal. And that is why, of course, it has lasted these 5,000 years or so. Skara Brae. Devonian limestones. Remember I mentioned in the south of England, you have marine conditions, you have limestones. It's quite old, so often we refer to these as marble. And this is a common ornamental stone used, so the top left in London, for example, and the paving for the Burlington Arcade in Piccadilly, London, you see is Devonian limestones. And can you see in the center, you have beautiful expressions of Devonian corals there. Bottom left, you have the ornamental limestone from St John's Chapel in Cambridge, and on the right, the Natural History Museum in Oxford. So Devonian limestones, yeah, which we use very commonly as an ornate stone. Right, now we move on to the Carboniferous, but I think this is probably a good time to have a break now. And then we'll just, in the second half, we'll talk a little bit about the Carboniferous and the Permian, which are our last two periods as part of the Paleozoic. So a short break, time to have a very quick comfort stop, time just to check your tea, which you might have had boiled 40 minutes ago, or time for any questions. That's great, Mary. That's great, Mary. So I would probably suggest another 20, 25 minutes, and then we'll be just discussing the Carboniferous and the Permian, and then there'll be time for more discussion or questions, if you would like that.
Thank you.
Yeah. So this slide, which you can see now, this is the paleogeography for the late Carboniferous. So you can see the United Kingdom, frightfully happy now around the equator, nice and warm. So think nice warm seas or land parts, Amazon, jungle, the Congo. In the far south, though, we had a glaciation, actually a massive glaciation, you see, which covered much of Southern Africa, south part of South America, really covered all of India, covered much of Australia. But we're not bothered about that in the United Kingdom. We were, as you see, nice and warm. So, what sort of life did you have? Now, remember I mentioned the Carboniferous, oxygen levels were high. So this was, with the Carboniferous and the Permian, the culmination, perhaps, of life evolving now. We had very tall trees. We had lots of amphibians. We had the start of the reptiles, fish, sharks, massive insects, you see. On the bottom right, wingspan here of 70 centimeters. So a great time to be alive, especially if you were an insect. But if you weren't, you should really take your insect spray with you. So what do we get in the Carboniferous? This actually is a map. It's really all of the main limestones which we have within Britain. You are obviously very close and associated with the green, which is the Cretaceous, but we won't talk about that. The Jurassic or the Cotswolds. Here we want to focus on the Carboniferous and the Permian. And here I'm just focusing on the Carboniferous, for example, and classical exposures you may well have heard of in the Pennines, and so Malham Cove, for example, in Yorkshire, and in Somerset, the Cheddar Gorge. Yeah. Warm, shallow seas. Excellent for limestone deposition. So these are the classical exposures you might have within the Carboniferous limestone. So at the top, you see you have Cheddar Gorge, beautiful exposures, and go into the caves, lots of lovely stalactites and stalagmites. Go to the Pennines and Malham Cove, for example, and you can see on the bottom right, typical limestone paving, making beautiful casts here, lots of caves, shallow, warm, shallow marine conditions. And it makes a marvellous building stone as well. Going to Wales, there's quite a lot of this Carboniferous limestone here. So in the south, you see Pembroke Castle, in the north, a Carnarvon Castle. A lovely building stone for making beautiful castles. So mountain building in Carboniferous times. Now remember I talked about the mountain building collision of essentially England, Wales with Scotland and America. I haven't talked about Southern Europe. So here comes France and Spain, always late, of course. They're well over 100 million years late, but in joining with us, in joining with the rest of Western Europe here. But this is the collision of Southern Europe with America, Britain, and France. So collision of Laurasia with Gondwana. So again, at the collision zones, perhaps you might have deep marine rocks and intensely folded. So on the bottom left, you see examples in Cornwall. Densely folded rocks, all due to this collision. We give it different names, the Hercynian orogeny, the Vaskinian orogeny, and lots of different local names, but essentially it's just a mountain building due to this collision here. Up came France. They wanted to join with us. Very sensible, some might say, others might not. What do you get with a collision? We've destroyed now the oceanic crust here. So you might very occasionally, with luck, get some of that oceanic crust abducted onto land. And this is what the lizard is. If you've been to the southern tip of Cornwall, the lizard ophiolite is again just oceanic crust. It's a preserved example of oceanic crust thrust up onto the land with the collision of France here. And this shows some of more than the crust, but actually the bit of the mantle as well. So the bottom left, you see the mantle peridotite rock. It often is green because of the olivine in the rock. So I tend to sort of think perhaps the mantle's green, although we can't really see it down there. But you can see the mantle rock, and above that, the oceanic crust thrust up, and we see that in the lizard in southern Cornwall. We have lots of volcanics in Scotland here. So if you're sensible and you have a volcanic plug, what do you do with that? You obviously build a castle on it, such as in Edinburgh, Stirling, you see Dumbarton, and on the top left, see Arthur's Seat here, which is a Carboniferous sill here. So a lot of igneous rocks, volcanics and sills, especially around the Midland Valley of Scotland. Not only the Midland Valley of Scotland, but northern England as well. So this is the Wyn Sill, which you might have heard of here. The Romans obviously recognized it as a great place to build a wall, the Hadrian's Wall here. But again, it's hard rock. What do you do with that? You clearly will build a castle on it, as you see, with these castles in Northumberland, Dunsborough, Bamburgh, and of course at Holy Isle, the Windsill in northern England. So this slide, it's a cartoon, gives you an idea of what we talk about the Carboniferous coal basin here. This is really the Upper Carboniferous 300 million years or so ago now. So remember we had collision since in Silurian times. We have high mountains in the north, collision with North America. We have high mountains in the south, collision with Southern Europe. And in between, we had these rivers and swamps here. So a vast area going, you see, right from Warsaw, going, as I've shown on this slide, at least as far west as Boston, where you had these rivers and swamps and essentially this coal basin, Upper Carboniferous times. Now, at the start, we had the Millstone Grit. So this was deposited by braided rivers, coarse sandstones. Go to the Pennines. Much of the Pennines is made of this Millstone Grit here. You can see beautiful examples of cross bedding. So you can easily tell which way these rivers were flowing just by looking at the cross bedding. And you can see make excellent millstones. So you can go up into the Pennines and actually you can see right at the top that some of these millstones. And I was just amazed at actually how they often made these millstones right at the top of the Pennines. And then they had to get them down to where all the mills were. That was easy. You just have a couple of millstones, a log in between the two, and you just cast them down the mountainside. But make sure you don't get in the way of these millstones hurtling down the Pennines. So now we get on to the coal. See, the coal is shown in the black colour, the map on your right. I've talked about the Millstone Grit, which is in the grey. So now we're talking about the coal, really the Upper Carboniferous. Remember, really warm Amazon jungle, the Congo jungle, high oxygen, very tall trees. Typically, we had these lepidodendron trees. Go to Glasgow, and you can see in a museum this fossil forest. Actually, go on the seashore in Tenby, in South Wales. Again, the seashore is just littered with these stubs of these Carboniferous trees. The deltas, swamps. And when these trees died, fell into the swamps, they got buried, converted to coal. This is really where all of the coal comes from, at least in this country, and most of the coal from Western Europe comes from the Upper Carboniferous. It also makes a very good building stone, often slightly darker, slightly greyer than the Millstone Grit, which I've talked about here. But Durham Cathedral, you see, I'm sure you visited that many of these, Fountains Abbey in Wales, Caerphilly Castle, all made from this Upper Carboniferous building stone. So again, just to emphasize the point, hope wherever you travel within the UK or your local town, look at the stones. How were the rocks deposited? I said great conditions, really, in the Carboniferous. very high oxygen. Again, we had gigantic forms. I talked about the Eurypteres, I talked about the fossil trees. I am proudly announced, I think, the largest millipede of all time comes from Northumberland. So, see, you think about 3 meters long. Gosh, that was a long millipede here. So crawled around equatorial regions, swamps and coast, but came extinct during the period. Why did it become extinct during the Permian? Was this due to reptiles? We don't really know. But giant millipedes and the best fossils we have found are British. Right, now I'm moving lastly onto the Permian. Now, so this is the last period of the Paleozoic here. Here, most of the, let's say, the continents were joined together with Pangaea here, Gondwana in the south. Within this macro continent we call Pangaea. But you see, to the, let's say, east of Pangaea, called the Palaeozoic. This was essentially the precursor of the Mediterranean, which is now closing, of course. Yeah. You see the British Isles moving now north of the equator, so more around the latitude of the Sahara Desert here. But also notice this marine fairway which we have, which is quite important with some of the rocks, especially within the upper part of the Permian, which we have in Britain. So we're now towards the end of the Paleozoic. Life has evolved rapidly, and it was really, again, a great time to be alive, at least at the start of the Permian here. Rapid evolution of reptiles, of insects, corals, and plants. And our ancestors, how do you like these friendly creatures? The Therapsids, reptiles or mammals. The taxonomists apparently say they are mammals. Some might say they look more like reptiles, but it's up to you. But apparently these are on the evolutionary tree leading actually to mammals here. So these we find essentially starting in the Permian. What sort of rocks do we get? The granites in Devon and Cornwall. So remember I talked about granites associated with closure of the Iapetus Ocean in Silurian Devonian times. So these are now Permian granites, again associated with closure of the other ocean, the Palaeozoic Ocean, when France came to join us. We tend to think of these granites, you see Dartmoor, Bodmin Moor, Land's End, etc., or isolated granites, but at depth, it's really one single granite intrusion. And continuous, you see, to the ciliars, for example, which are essentially granites here. Again, makes a very hard building stone, Truro Cathedral, the granites of Tower Bridge here, and lots of granites in London, of course. If you go around London looking at your building stone, excellent examples of granites, many from Devon and Cornwall, many from the Scottish Highlands. And minerals associated with these granites, the hydrothermal vents, Cornish tin, especially associated with the flanks of the granite. Not really tin mined now, my understanding in Cornwall, but will lithium, for example, be mined? That's another story. I talked about time of the Permian. Now we are more at the latitude of the Sahara. So what you have sand dunes, massive sand dunes here. And these are examples of the rocks. You see on the right-hand side, you go to Devon, you see the red Devon sand dune rocks, which actually we call new red sandstone, but essentially it's bright red formed in desert conditions. Excellent examples you see on the slide of cross bedding. You can clearly deduce from that what was the wind direction at the time. The Permian desert sandstone. Again, quite a common building stone here, especially around the Scottish borders, for example, here. The Dumfries castles, the abbeys here, the Carlisle, a lot of Permian sandstone said around north part of England, southern part of Scotland here, but in desert conditions. But you can go offshore, for example, go into the North Sea of Lincolnshire, Yorkshire, East Anglia. Here you have Permian desert sandstones here. And you can see how it essentially there's a transition. You have the highlands around London. We call it the London Brabant High. So these were the highlands. And sedimentary rocks, actually sands, pouring off these highlands in the northeast direction to the alluvial fans, fluvial plains. And then we had these sand dunes. And then the sabkas here. And then these desert lakes. You can see this very well going out into the North Sea. Remember, I mentioned you do have this marine lane here, especially in the upper Permian. So here we have Permian limestones, warm, shallow marine conditions. And in Yorkshire, York Minster is made of this. King's College Chapel is essentially made of this. Westminster is essentially made of this. It's a beautiful buff-coloured limestone. End of the Permian, so shallow marine conditions. But also do you have, especially with deserty environments, shallow marine, you have drying out of the marine, forming salt, evaporitic salt mines. You can go into many countries and you can go into these salt mines. And examples of more recent ones, due to the drying out of the Mediterranean, in Romania you see in Sicily. If you want to, you can go to a Siberian salt mine. You have beautiful salt mines there. But we also have lots of salt mines, of course, in England. And this is an example from Cheshire, Permian salt mines, drying out of these inland seas, thick deposits of salts. Now, salt is really a very odd sort of rock. It's so light. Therefore, it flows. It's lighter than any other rocks. So it forms these pillows, diapirs, teardrops. So looking at a cross-section of the earth, you see these sort of mushroom shapes formed because the salt is flowing. We see this very clearly in England and the North Sea. And this is what you would find, for example, in a cross-section. These salt domes, and these make beautiful salt traps for oil and gas. So this is the Permian salt moving. So forming structures, forming seals. This is where and how we get most of our gas reserves from the North Sea. So we have this basin full of gas fields, you see, from onshore England, essentially going into the Netherlands and even little bits in Germany and Poland. But it's mainly the southern North Sea where we have the main large fields. So gas fields associated with salt formed the drying out of the inland sea. We have hundreds of gas fields. So essentially, England, or rather Britain, and the Netherlands were self-sufficient in gas. And we still have got a lot of gas still in these gas fields if we were allowed to extract them. So we could easily have at least half of our gas coming from the North Sea. Right, now we're virtually at the end of our story here. So the end of the Paleozoic, what do we have? We have the Permian extinction, what we call the Great Dying Event. You can see oxygen levels suddenly plummeted, temperatures went up rapidly, the CO2 went up a lot as well. So carbon dioxide increased, rapid warming, low oxygen, and a lot of other points which I've listed here, which really makes it not a very happy place for life. See, 95% of life perished. A lot more than at the end of the Cretaceous. Not a lot happened at the end of the Cretaceous. Okay, the reptiles died out, or at least the land reptiles died out, but the birds were completely happy, and so were the mammals. But the great dying at the end of the Permian. So what caused this? Now, I hate to blame this onto Russia, but I'm afraid I have to. The Permian extinction, the results of the Siberian flood basalt, Siberian volcanics. An area you see greater than Europe. So much of Western Siberia and was really covered by volcanics. And so this essentially changed the atmosphere of the whole world. So that is why we had the great dying. So the demise really of the Paleozoic or ancient life led to a new life. So it wasn't all bad news. We had the demise of the Paleozoic, but what then did we have? We had the dawn of the Mesozoic. The age of the dinosaurs, but there were the subservient mammals, and there were the birds. But very much so the age of the dinosaurs, and that's another story. So thank you for listening.
Thank you very much, Martin. If you could stop sharing, I'll pause or stop the recording, and then we can do some questions.
Right.